So I'm just going to do a couple quick examples following up on today's class. So we did part A from the projection. Let's take a look at part B real quick, just for a nice review. So you might think of V as the vector 3, -2. So this is a two-dimensional vector. U is the vector 1, 6. So if I were to visualize these, 1, 2, 3, -2. So there's V, and then 1, 6, 4, 5, 6. So we're kind of way up there. All right, and so this is one where if I extend that U vector, the projection goes down this way. I'll do that in red. So really we're talking about that edge there for your projection. So let's verify that, see if that works out right. So the projection of V onto U is the formula U dot V over the magnitude of U squared, that scalar all being multiplied by the vector U. So remember, essentially what this does is it trims the U vector down to its unit vector in that same direction and then multiplies it by that scalar, which in this case, it looks like it should come out to be negative if we are predicting this correctly. So U dot V would be 3 times 1 is 3 plus 2, -2 times 6, so minus 12, giving us -9. The magnitude of U squared, well, that would be the square root of 1 squared plus 6 squared squared. So 1 plus 36, 37, square root of 37 squared, giving us 37. So then the projection of V onto U would be -9 over 37 times the original vector U 1, 6, which would be -9 37ths, -54 37ths. And that actually, if you look at those coordinates, that seems to match up pretty good with our prediction, at least by an estimate, and you could do that in Desmos 3D to verify. So just wanted to show you that as a nice little review and follow up. All right, the next one, this is the one where I was saying, what are these projections used for? Well, this example, we briefly mentioned kind of the idea. Essentially, you've got the ship traveling at the 15-degree direction, right? But the current is coming in at a northeast direction, which would be 45 degrees. So it's getting some help from the 2 knots of the current, but it's not getting the full increase in the knots. If it was in the exact same direction, then it would just be the 20 knots plus a 2-knot current, giving you 22 knots would be the actual speed. However, this one, since it's going at a different angle, it's only getting a component of it. And so that's where the projection shows up, right? You drop your 90-degree angle, and so you're finding a right triangle, and essentially you're trying to get the, like, what portion of W is actually helping in the V direction. So if we're labeling this here, that projection vector would be the projection of W onto V. So we're trying to find essentially what portion of W is in that V direction. All right. So it's kind of like finding the cosine of that, but I don't think we quite have enough. Actually, we could do this. We could do this with the projection or the component formula. So let's just write this out, just the different formulas that we kind of have to choose from. This would be the projection of W onto V. So we would have V dot W, but remember the magnitude is the magnitude of the one you're projecting on. So it's being projected onto V. All right. Or that scalar, because it's actually kind of finding like, oh, well, what is the component of it, the kind of magnitude of that side. We could actually kind of do that with a cosine as well, but we'll get to that in a second. I'll show you. So you could also think of this as V dot W over the magnitude of V times the V vector over the magnitude of V, because in that case you're finding the length of that projection, and essentially that's the component of it that you're increasing. So the length of that vector. So that right there that I have highlighted, that's the component of W that is going in the V direction. That's really what we're looking at in this problem, to find, like, of the two knots, how much of that is coming from there. All right, well, so let's do that calculation. So V dot W. Oh, actually, see, this one we don't know. We kind of need to know the alternate version. So that would be the magnitude of V. And I did say a minute ago about using the cosine. This actually does show up because we don't really have the components of W. We could find it, but it's already built into our dot product. So the magnitude of V times the magnitude of W times the cosine of the angle between them. This we do know. We know this because if the current is 45 degrees, but then 15 degrees of that is the ship line, so the difference between them ends up being 30 degrees. All right. So the magnitude of V is the 20 knots. The magnitude of W is the 2 knots. Cosine of 30 degrees. So in this sense, you're getting kind of only a portion of the 2 knots, because you're going to be multiplying that by cosine of 30. All right, so let's see what we get there. 40 cosine 30 degrees. 30 degrees, remember from your unit circle, that would be the x coordinate. So that's root 3 over 2. So 40 root 3 over 2, 20 root 3. All right, and actually I realized if I had just plugged in from the beginning, it could have had a nice little shortcut, but that's okay. We can still make that work because the magnitude of V, remember, was 20. So putting in our the component of W in the V direction, putting that formula together, we end up getting 20 the component of W onto V is equal to 20 root 3 over 20, which is just root 3, which is approximately 1.73 knots. So remember we were saying, oh, wait a second, if I'm getting 2 knots of current, but I'm only getting a portion of it in that same direction, that's why we're getting something a little bit less than 2 knots from that, because it's only getting a portion of the 2 knots of help. So the total speed, I don't know if that's quite the right word, the total amount of knots that the ship is traveling would be 20 plus 1.73, giving us a 21.73 knots in the 15-degree direction. So I'm going to zoom out there so you can kind of just see that beginning to end. You can pause it, take a little recap if you wish. And I did say if I plugged that in from the beginning, it would have worked out kind of nicely, actually, if I had just done it this way. I was doing it in pieces, but if I just plugged it all in, that would have been 20 times 2 cosine 30 over 20. The 20s cancel out. 2 cosine 30 would be 2 root 3 over 2. The 2's cancel out. You still get your root 3 either way. Same thing there if you just did it all at once. All right. And while I'm making this video, I'm just going to go to the next page and just kind of talk about this. It's kind of the same idea here. This example is all worked out, but for work, the formula of work would be like the force times the displacement. That says distance. I actually like displacement better because that allows for kind of the multi-directional stuff. So the force times displacement. And so if those are vectors, force is a vector. Oh, that should really have an arrow over it. For force is a vector. And then PQ is a vector. It's kind of the same idea that you're only getting a portion of it. So if you're pulling this wagon with a force of 8 pounds, right? But if you're standing up tall, you're kind of pulling in a diagonal direction. So kind of as a projection of that 8 pounds, you're really only getting kind of a component of that, which is why that would be 8 times cosine 55, because you're not getting the full 8 pounds of force, because some of that you're pulling upward, but the wagon is only moving directly horizontal. So essentially you're finding the component of the horizontal force, and then that would be times the horizontal displacement, giving you the 229 foot-pounds. All right. There is another one here. Maybe you can check that out on your own, kind of based on these same directions. You got a force vector. You've got your displacement vector would be between those 2 points, and basically just plug it into your work formula. It's kind of a straightforward calculation from there.